This
Thanks,
conference will
Bobby.
now be recorded.
Okay, thanks, Bobby. One of the reasons that I've been listening into the business workshop discussions is because I believe it's one of the most important things that ODSA can work on in the next year that'll be unique in terms of what we can help the community and the broader market with in terms of establishing an open chiplet economy. And there was a discussion a couple of weeks ago, kind of drawing a parallel with, I think, PCI-SIG, where it was important to have some sort of agreed upon, centrally supplied, even third-party neutral supplied checklist by which a vendor could then come and either self-certify or get a third party to certify their chiplet against, so that when a company is selling a chiplet, the vendor knows that it meets certain criteria. And that struck me because there's an interesting parallel between that and some of the work the OCP community is doing in other areas. And it is an area where perhaps the OCP can be a catalyst because we already have existing precedent and third-party programs. That's why I was wondering at some point if the community here could develop a checklist for against which a chiplet vendor could certify that their chiplet meets the criteria that is needed for integration in a SIP. And the community here could decide on what that criteria is, and there's common agreement. Then the OCP, of course, that can become a contribution to the OCP. It becomes a spec in the open or a checklist in the open. And then through our Experience Center program, we can look to find chiplet vendors that want to self-certify against that community developed checklist. We can also at some point look forward, maybe in the future, if we think far enough ahead, that there's even a section on our OCP marketplace for chiplet vendors to offer their wares, and they would have potentially have a badge if they've gone through the checklist. The parallel here that you may not be aware of is our OCP Data Center Ready Co-location Facilities program. It does precisely that, where the problem that's being solved is today, let's say a data center operator, one of the large hyperscalers or another one, wants to go and potentially rent space in a co-location facility. They each come with their own different checklist. And the facility provider has to certify against that checklist for each of them. And of course, each of the checklists are different. So there's a fair amount of delay and costs in certifying for each potential customer. Now, within the OCP, there is a movement for the hyperscalers along with the rest of the community to come together and create a checklist that the data center co-location facility operators can certify against once, and the data center operators can trust that that certification is going to provide what they need when they go to put OCP recognized equipment into that co-location facility. So I just wanted to put that on the table for the community to think about if that makes sense at some point to generate that kind of community-driven checklist that can be housed at the OCP, and the OCP can build a program around. So that was my thought. Does anyone have any thoughts or comments on that?
Anybody have any reaction? Mike?
Oh, sorry.
Oh no, go ahead, please.
Well, I think the challenge is the breadth of functionality that you have in a chip is it's hard to like, I guess you'd have to make it quite a narrow scope, and if you did, then you'd have to scope the functionality as well. So
right, and I was wondering if it's possible to have from the experience of the community, scope 3 or 4 or some number of prototypical configurations, architectures that you test against, something like that, rather than trying to boil the ocean, right? So maybe not narrow to one.
So are you talking about standard compliance to a bunch of wires, or more the chiplet itself?
I wasn't saying they would have to be towards bunch of wires. I think bunch of wires could be one of the things that a company could standardize against. I think it would be open to whether it would be the interconnect, the chiplet itself, what would make sense, right? Put ourselves in the shoes of a chiplet purchaser. What would they want to know from the chiplet vendor? What would be that checklist that you would go through? Environment.
Yeah, no, I think it's a good idea. I do understand that, the point that was made that it's a very large ocean there, right? So, but we need something, right? So that's the other side of it. So it may not be perfect, but I would say that this is obviously something, and the customers are going to be interested in.
Right, and if this isn't the community to help narrow the scope and pick a few starting points, then I don't know which one would be, because the expertise is here in this community.
Hi, this is Suresh. A couple of thoughts I had, at least I want to throw it out there and see what the others thought. Some basic stuff like, what are the minimum things you require for configuring chiplets? The other is, for example, if you're integrating multiple chiplets, one thing, if you're getting it from different fabs, then the bump structure is kind of critical. So are there a few things like that? Beyond the functionality and all of that, just if you're putting more than one chiplet on a SIP, there's some minimum assembly things and configuration things that are common that you need across all of those chiplets as a starting point. Any thoughts?
I think it's there's too many, there's not a narrow enough scope for, I mean, well, so what you might consider is what's something that's used a lot. Well, RAM, right? So maybe you could do a RAM chiplet standard. And I would suggest a place for that would be JEDEC, because JEDEC already does RAM, for example.
Well, you're aware we already have a relationship with JEDEC, and we're doing precisely that with CDXML. And so if the community here were to put an open spec together, we could certainly approach JEDEC to make it a formal standard. But if you look at the other parallel I drew for you with the data center ready co-location facility program, today that's not necessarily gone to a global standard, but it's still being used. And it might start that way, that it becomes a de facto in use checklist that people like, and then it gets picked up by JEDEC, and we can even approach JEDEC on it. We have the relationship with them.
I guess the point that I was thinking was there probably just a handful of. So sure, yeah. To be on the positive side, I would say there are a handful of chip implementations that are common enough to warrant a chiplet specification. And one of them that comes immediately to mind would be RAM. And I guess the other one you might think of would be NAND, right? So non-volatile memory, and then maybe outside of that, it's not clear to me.
No, I think you can sort of, I mean, I like the idea of focusing on common functionality. You got to have flash, CPU, NIC, whatever we expect as a common class of chiplets. And zeroing in on Suresh's idea that, hey, let's focus on integration is not a bad place to start. And using CDXML as the vehicle for description seems reasonable.
Yeah, I think even at the processor level, you run into trouble, because I doubt that, because they're of the how do I say this diplomatically? The differentiation between processor vendors, so what are they? Well, it's x86, and then AMD and Intel, and then there's the RISC camp, and then there's the ARM camp.
You're not trying to capture the functional variation, right? I think the intent here is simply to say whether treated as a necessary but not a sufficient condition. Is there enough information to easily integrate the chiplet?
I think, Tim, I think I understand what you're saying, and I think I generally violently agree. I think perhaps what Tim is getting at is a primary challenge in this space is that if you want to define interoperability, you also have to define functionality with a very sort of specific and concrete, sort of set of requirements, much like JEDEC does for DRAMs. And I think what Tim is just pointing to is that it may be very, once you're outside sort of the scope of something that is considered a commodity part, it may become challenging to very specifically and concretely nail down all the functionalities, features, sort of requirements, and so on and so forth, in a way that doesn't contradict the differentiation that people are looking to make. Tim, did I capture your thought?
Oh man, Elad, you rescued me. Thank you. That
No
was
problem.
that's exactly what I was trying to say.
I think you're solving a problem that Cliff isn't advocating for us to solve. We're simply saying, if you start with, if I understand the proposal, it is to describe the ability to functionally integrate a physical chiplet. Start there, physically integrate a chiplet, and leave the functional interoperability to a system architect or somebody else to figure out.
I think what Tim and I are probably, the input we're both giving is not that this is not a good idea. It's just that it may prove to be very challenging to do even the more limited thing you're describing without actually sort of, this more concrete, hey, here's a representative functional partitioning that, that we are thinking of. Because obviously, even the physical part of it very strongly depends on what functionality you're expecting the thing to do. So that there may be a subset of things that, it can be, that one can define, and I don't think, it's just, where that boundary is obviously the question.
Yeah, but overall, I don't think I'm as pessimistic as you guys, because I think there's room for a necessary checklist. May not be a sufficiency condition, but there is that if you fail this checklist, you definitely can't be integrated. There's room for that.
Yeah, no.
So if we
right.
I was just going to say, if we take PCI SIG as an example, right? I mean, they're a very successful example. There's industry involvement. There's a standards body. There's, it does go into, accelerators and everything else. But the basic premise is, first of all, can we just interop with each other, right? At a simplistic level, right? And the same sort of thing is done in optical modules or whatever, in all these data centers. There are standards that are industry, OFC, et cetera, where they sort of try and define something so that, when you plug it into the connector, the damn thing connects, right? So we're defining a PHY interface. I mean, that's where we're coming from here, right? Or whatever, right? And at a basic level, there has to be a way to address this interoperability, right? And without getting bogged down in what are all the things that you could possibly do with this standard, right? And so that's I think that's where I think some of us are coming from, at least, is you need to start doing something. And
Sure. So what the example for that, Cash, I believe, it might be a UCIe, because UCIe, and I'm not suggesting that, it's just an example, but there is as part of UCIe, there's a compliance aspect, and they're talking about developing test golden chiplets, and to be able to certify that your chiplet connects to the golden chiplet through that UCIe interface at the different levels that they stipulate, right? Because they have a link layer as well as just the raw mode and so on and so forth. So,
right.
But, and in fact, they do have a bump out that is defined. Although I think it's more, the interoperability is more at the electrical level, you know, which is so it's so maybe, but that's an interface specification. It's not doesn't go beyond a very limited set of functionality, and it's already in. So what you might say is, well, as part of a bunch of wires, you might have an interoperability. Sorry, I'm ignorant. You could have an interoperability portion of a bunch of wires, but I don't see it going beyond that function of the interface per se.
Hey guys, just a thought came into my mind here. This interoperability problem, you know, part of it is to get two suppliers' chiplets down onto a module costs quite a bit of money in the first place, right? You know, just to do an interoperability test. So bunch of wires can go up to 25 millimeters, if I understand correctly.
Wait.
So
Yeah,
can't we do? I'm not sure if any of the connector guys are on, but couldn't we do a really tiny mobile phone type miniaturized connector where everybody says you put your chiplet on this with this connector and you can plug it into somebody else's chiplet and do an interoperability just with a tiny interconnect, so that there's no cost of having to fabricate PCBs each time or substrates each time to do the testing or the interoperability testing. Is that something worth considering?
Yeah, wait. I think we're burdening the checklist with a function it didn't want in the first place, or Cliff didn't. We're not talking interoperability. We're not talking a guarantee of interoperability. We're simply saying, think of it as, hey, have you thought of these things when you're readying your chiplet?
All right, yeah, apologies. I have just jumped into this call late, so apologies.
No, it's but as many ODSA discussions, but we tend to sort of zip all the way into interoperability. And I want to point out there's a huge jump between zero and full interoperability, and that maybe a checklist can help us bridge at least with saying, okay, did you think of these things, and what are the values you have?
Right, fair enough. Yeah.
So again, I want to jump in here for a second. Rather than talking in abstracts, can we not think about the mechanics of actually putting something together, which is two or more chiplets, and start from what does it take to put them on a SIP all the way up the stack to what is the functionality required, and you can at least identify what are some minimum things that way. So you can stop at whatever level is comfortable, but instead of this is an abstract discussion going in too many directions.
And are you by any chance volunteering? I mean, I don't want to punish you since you brought up the idea, but are you able to take a first crack at it with Cliff and me? Or I think David and Jawad said they have some ideas too.
Absolutely.
Okay, let's go off and make one proposal and bring it back. It's easier to sort of shoot down a bad idea than an abstract discussion. And then Marek can, I'm assuming Marek will help as well. So
Yeah, I'd be happy to.
Okay, let's. That's a good way to let's take a tangible example and see whether it has any merit. Cliff, is that an adequate bow on the thing?
Yeah, I like it. Let's schedule put something in the calendar.
Okay, so Suresh, David R, Jawad, Marek. Anybody else want to volunteer to take a crack at this idea of a list? Anybody else interested?
Hi, Duffy. It's Mike here. I'm in a bit of a noisy place, but yeah, I'll join that.
Okay.
I don't know if you can hear me.
Yeah, I can hear you. Anyone else? Going once? Twice? Okay. So Marek, this could be something we do in the business work group, or that part of the ideas that something that we pull off.
Yeah, I think that that would be a good first starting point, and then we can also see to do kind of the recap of the business or company talks as a separate item.
Fantastic. Okay. Then what I want to do for the next 30 minutes, I think we've made some, okay, let me just cut to the chase and show you what we have. So I think we made decent progress. I'm glad Ram's here. I'm glad Tim's here. Elad says he's going to leave in a bit. So if somebody could volunteer to take notes if there's anything that comes up, because I can't. So I think we're nearing a pretty decent milestone. Wait, one other question. If I go to full screen mode, can somebody stop me when it's 8:55? Is there anybody who's going to stay till the end? Cliff, are you going to be here?
Yeah, Poppy, I think I will. I'm just checking to see if I'm being called to another meeting, so likely yes.
Okay, so Tim or Cliff, one of the Canadians, please stop me at 8:50, 8:55, because I'm going to go into full screen mode and I can't see my clock.
Okay.
So I think we're nearing a really big milestone for us. We are in the process of, I'd say, specifying a complete ODSA link. And when I went back from a couple of years ago, we're remarkably close to where we thought we'd be. When we started a couple of years ago, we thought that an ODSA link would be a diport controller sending AXI packets over a BO-PHY. And for the most part, we're not too far away from that thinking, right? We've got a BO-PHY, which Elad has led the charge on. And now the two new elements are a sideband interface and a transaction and link layer protocol spec from David. And in some sense, you could still have a diport controller riding on top of the TLP. So the thing I want to walk you through for the next 20, 25 minutes is really simply to point out that, hey, I think we're in pretty decent shape. For the Bo data path, 1.0 is released. It's in silicon in multiple devices. 2.0 is in a stable draft. It's going to be presented to the incubation committee in the very near future. Transaction and link layer is the 1.0 draft is stable. Hopefully we get to present to the server project next week and the incubation committee as well at the same time as we do the 2.0. And then you need this idea of what are called profiles to describe transactions. And so we've got a Veyron profile from Ventana, a diport profile from NXP, and I think Brian from VeriSilicon will have a couple available, maybe as drafts, if not as full 1.0 specs. On the sideband PHY, we have a stable sideband PHY draft in Bo 2.0, and we also support I*C, and I'll get to that in a bit. And finally, I think the last piece of the puzzle, we now have a handle on, I'd say, a fairly good definition of the control logic. We're going to borrow heavily from D matrix, especially Ram, the sort of heavy thinking Ram was done in this space. So let me stop there. Any questions, any thoughts? Okay.
One question I would have is like how we want to position all these elements. Like, is this going to be? Is there going to be like kind of a chart saying like you can use these things in the following ways? And it's just like they have like basically different numbers, and I wonder if like for somebody coming in now that they realize like all of these interoperate.
It's a good question. So this slide deck is my first crack at that issue. And but you're exactly right. I mean, is the feature set in Bo 2.0 a la carte or between Bo 2.0 and 1.0 a la carte? How do they interact with the features in the TLP spec? Is a really good thing. Is a really good question. So really, I'd say, we're looking at an ODSA link. It has 4 components. It's got the Bo specification. It's got the TLP specification. It's got the management interfaces and this link controller. And what I'm going to do is just sort of zip through the status of each, at least the first 3 in a really high level. So the data path file is something that takes bits from the TLP layer and pushes it over the die-to-die, over the substrate, out of the die into the substrate, right? And everybody has seen this diagram in terms of what the Bo file looks like. The basic unit definition is a slice. We've got 2 extra bits. It's a unidirectional file with a differential clock between the communicating chiplets. And what we now have is a whole bunch of Bo modes on laminate and advanced packaging with different kinds of termination. What's new in the Bo 2.0 is the 384 and 512 512 definitions for slices, but the 32, 64, 128, 256 were in the 1.0 spec. There's also a whole bunch of stuff on initialization training, testing. And what's new also, we've got this notion of half-bit slices in the 2.0, so 8-bit slices, power management, and a sideband interface, and a whole bunch of things. And I think Elad's done a talk on Bo 2. I think he did a talk on Bo 2.0 recently. So anyway, the whole point in this is I think we're in a good place, and we're just going to iterate on Bo in terms of adding features and stability, etc. So when you come to the link layer, right? Here too, I think it is reasonable to say we have a 1.0 spec. And I just realized that I don't have, really what the link layer does is it fits into this model that your die-to-die link is an agent on the internal bus on one of the chiplets. And what that die-to-die link has is it has a transaction layer that takes bus transactions, puts them into link layer packets, and the link layer is the actual direct link between the 2 communicating endpoints and transmits them over the file layer. And almost all this work is done entirely by David Kruckmeyer from Ventana. And what we hope to do is have what I'd say is a 1.0 spec. This proposal has been stable largely, and we're doing sort of he's doing sort of the final crossing the T's and dotting the I's. So really, the top of the link layer gets its input from the internals of the chip, and its output goes into the file layer. And on the RX side, it's in the other direction, right? Fundamentally, what you need to do is the link layer, and the transaction layer have to arbitrate between the various classes of traffic. Each type of bus is one class of traffic transaction class. And it also has to provide some degree of where there is a credit-based mechanism between the 2 communicating chiplets. And the link layer has to it requires bidirectional communication, even if a link is unidirectional, to implement this credit-based mechanism. But again, I'd say that there's enough there to implement something. And the interface between, so the transaction layer packets, it's a very sort of a very networky structure, that you have a transaction layer packet which then gets packed into link layer granules, etc. right? And so this spec is on the Git repo. You're welcome to download it, read it, and if you have any comments, pass them on to David Kruckmeyer or me or anybody else. So what you need on the link layer, unfortunately, I don't have the NXP profile, is at the top, you need something that says, this is the class of traffic I support on my bus. And Ventana's profile supports AXI 5 Lite and the Chai profile for cache coherence for coherent traffic. And fundamentally, so the basic structure of the link layer spec says, look, I'm assuming there's a message-based interface, and I'm taking that message-based interface and converting those messages into packets, into link packets and assembling them. And each one of these is a profile. So this bus is, the Ventana interface implements a combination of an AXI 5 Lite profile and a Chai profile on the interface. NXP has a separate profile called DIPort. So the expectation is that for two sides to interface, for two sides to exchange traffic, they have to have the exact same profile. And these profiles will not be a part of the TLP spec, but will be published as separate documents. Okay, let me stop there and see if there's any questions so far. Okay.
Maybe one question. It seems like so far the way we're creating these profiles is to see, like, based on what use cases companies see, and then putting that into this open specification as another profile. Is there in the future a thought of maybe like anticipating the kinds of like traffic and load that we will have and generating profiles even before they're being used in a specific product?
So in some sense, there is some effort at generalizing this in the following way. Sort of there is one slide I made that I should have. Give me 1 second. Let me see if I can find. So the general model for this is that they're looking that there's only a finite number of interfaces. I'm going to see if I can find that slide that I'm interested in. That there's only a finite number of interfaces, and most of them come from open standards driven by ARM. So there's only a finite number of interfaces that matter here. So you kind of know, so your decision is really on whether you want to support that interface or not. Does that make sense? So you kind of know, here it is. So in some sense, you kind of have an interface agent, and the number of interface agents is finite. SOCs are built using either some kind of an AXI interface agent, and most of them come from ARM. So you kind of, the thinking here is you define something called a bus profile variant, and that bus profile variant tells you how to map the traffic from that bus onto a ODSA link. In some sense, what you're doing, the bus profile variants are the sort of attempt to do what you want, Marek, which is to sort of say, hey, this is a range of things that could happen, and yeah.
I was just going to say, I don't think that's what you're saying is accurate, right? The whole focus of the link layer has really been on like processor to processor type communications, right? And managing processors. And if you look at the real world, you're talking about buses and things like that. I can name PCI Express, right? I can name Ethernet or interfaces, right? USB, JESD, right? That a lot of people want to send over a die-to-die interface, right? With coherency or there's some special timing required. So there's a real world out there where that's the kind of questions that people ask, not how do I do a Chai interface. I understand the market for a Chai interface is very narrow, but there's a lot of innovation going in there. But there's also a different world where I would say that, if you gave me a list of buses that people are interested in transporting, it would look quite a bit different than what ARM is proposing, right? I'll just leave it at that.
I'm not arguing. So wait, we're debating two different things. There's a list of what we ought to do, and there's a list of what has been done in the spec so far. And I'm talking about, my focus here is on what has been done in the spec so far. And what has been done in the spec so far is this concept that we're defining the interaction between chiplets is based on the concept of an interface, which is a channel-based interface, and mapping the logical channels in that interface onto transactions on the bus. So this is simply a model for how data is transported across the link. It's not saying that this is the universe of all the things that AXI is the universe of all the things we need to do. So what we have is a profile for different classes of AXI traffic and CHI traffic. If you're making the case that, hey, we need to make these models for other kinds of buses, absolutely. PCIe, I'm kind of less sold on, because I think it's almost entirely going to be UCIe centric. But at least for the other kinds, we need to create a profile for the other kinds of buses. But the basic model here is I have an interface with different channels of logical data, and my profile maps those logical channels onto bits on the bus, onto transaction layer packets and bits on the bus. Kash?
Yeah, I guess I'm sort of looking at a different market then.
Right, but what's your heartburn? And maybe that's the point of this meeting. Is what's your heartburn with if I have a USB bus, figure out what the channels are, and then figure out a mapping from the bus into transaction layer packets? What would you do differently?
No, I don't know. I haven't really been focused on link layer development. I have attended a few of the meetings, but I do think that, yeah. But the focus that as I gathered was much more on the CPU to CPU kind of or intra CPU kind of busing. Yeah. So you made a point about PCI Express, and that you're not interested in that because that's going to be UCIe.
This is something. Yeah, go ahead.
Well, that's what I heard. Maybe that isn't what you meant, right? So,
right.
if you have a bus that isn't really, you can't really offer a PCI Express solution to that's competitive with some other bus, then PCIe is probably the most. PCIe and Ethernet are probably the most important two interfaces, sort of potentially in the data center, right? And the data center is one of the key things that's driving a lot of this die-to-die requirements. So anyway, that's my 2 cents. Yeah.
So just so we're clear, right? I mean, what the transaction layer, what we're talking about is a model that the transaction layer assumes. And so if we want to model if we want to put a bus that hasn't been covered or an interface that hasn't been covered, the assumption is it can be modeled as a collection of logical channels and virtual wires. Now, if there's a bus that breaks that assumption, then we might need a different interface model to transport packets on the transaction layer. This is simply an assumption of how the bus is modeled. And under that assumption, we've got profiles for AXI traffic. Should we have profiles for USB, Ethernet? Absolutely. But we need somebody to develop them, right? And so the question here is or the debate here is the basic model by which we're assuming an interaction with a bus broken? And I haven't seen any evidence that it is. I think it's a reasonably valid model to think of a bus interface as something with a collection of logical channels and virtual wires. You see what I'm saying?
I see what you're saying. I think that the devil's always in the details, and PCI Express is a you know, and CXL are very complicated, and right now, if I was doing a solution, I'm just looking at it as a customer, not as a vendor here, right? And I see, you know, the foundation of UCIe is PCI Express, right? So it obviously does a very good job in that.
Exactly.
And if you come and look at ours, we don't. So if I am doing a PCI centric solution, then naturally they're going to gravitate to UCIe, right? And now you have a bigger issue, which is okay. If a customer says, "Well, oh, Bo doesn't do UCI, doesn't do PCI Express well," or however you want to define it, are they going to mix and match in a given SIP? Are they going to mix and match, do you think, a bunch of wires and UCIe, or do you think they will design sort of one bus or go after one sort of ecosystem? That's the concern that I have, right?
Well, that's an easy answer, right? I mean, if you look at chips out in the market today, even nobody who supports UCIe has disavowed their internal bus. They're already going. There already are products. The product plans call for a separate internal bus and a separate outward-facing bus for external IP. So whether there will be two different chiplet interfaces within a product, I think that question's been asked and answered. That it isn't necessarily going to be a homogeneous interface. But so anyway, sorry, somebody have a question?
Yeah. So I think my point is, if I'm now going to develop a chiplet for this wonderful open chiplet ecosystem, and I'm going to spend $10 to $20 million developing one, I'm going to develop one that obviously supports Bo and UCIe, or develop two products. How's that going to work?
Well, so I think so my personal take is way too much of our discussion gets hung up on interoperability and how do I build one universal chiplet. I think let me focus this discussion on, can you establish an ODSA link between two chiplets? And then we come back to
okay, all right,
yeah,
okay,
right?
That's
because,
fair enough. Sorry.
Yeah. Otherwise, it's very easy to get hung up in, is this interoperable with that? And, you know, can I build one universal chiplet? And the good news that where we're at is, at least for a fairly decent set of use cases for data disaggregation, you now can build a complete ODSA link to that. You can sort of say, here's the BO5, here's how the BO5 talks to the link layer, and here's how the link layer talks to the internal system bus, which is no small accomplishment in my mind. Right? And so
fair enough.
Yeah. So the sort of last piece of the puzzle is in my head, which is coming together, is this notion of the control file. And we'd have a proposal for a Bo sideband in within two communicating chiplets, which is an alternative. So there's two. The original Bo spec sort of said, hey, there will be a management interface, and I think we added a sideband PHY proposal in the 2.0, and the link controller is going to be built on the sideband and sort of follow up with the I2C, right? And so the last part of establishing a bidirectional link is a link controller, and here's where I think we made a fairly decent amount of progress thanks to some discussion in the link layer group, and I think we're going to steal shamelessly from D-Matrix, right? That we're essentially focused on how do I bring up a unidirectional link between two communicating chiplets, and really it will say the control path spec really talks about how do I bring up a link, a unidirectional link between two communicating chiplets, and if there's a bidirectional link, it's two separate bring up processes. Then a link itself, a sublink itself, can be a collection of slices. So you will need at least one controller per group of slices that come in. So if you assemble a group of slices into a link, then each separate link needs to be brought up independently, and a pair of communicating devices may have multiple links between them. Now, the big thing here is that there's going to be we assume a lot of training in the process of bringing up a link, that you're going to train a slice, maybe do slice repair, that you're going to do training of the link as a whole, and you're also going to need the ability to bring down a link and bring it up again, retrain it when you see operation errors during operation. And on top of that, we think that there's going to be there might be room for optional vendor specific tests between these. So really, what a link control path has to do is do 4 things. The two sides have to discover one another. Once they discover one another, they have to initialize communication. And on top of that, they then have to test and train the link, and finally bring the link into operational state. And that's a sequence that the link control path, link control protocol specifies. So essentially, init is where the two sides have discovered each other. And we're assuming that once the two sides have discovered each other, that in this case, we're assuming that the two sides will discover each other through a sideband. We will eventually make room for a 1.1 specification where the process will be specified in I2C and I3C. The most important thing is that all the transitions, state-to-state transitions, are triggered by the RX, but executed by the TX, right? Except for the fact that if you want to break an operational link, that can also be triggered by the TX. And test is a huge state where you have a collection of multiple tests designed to establish the link. But the fundamental point is discovery, establishment, test and training, readiness, and your operational. Those are the 5 states, 5 top-level states we're defining in this. We're likely to define in the spec. On top of that, in terms of tests, we're going to say there's going to be some mandatory tests to configure redundancy. Maybe there's room for optional tests. The order will likely do a reference order of tests in which you need to apply the test. You bring up the slice first, and then bring up the component slices in a link. And there will be room for proprietary tests which are outside the scope of the spec. And link bring up will be specified by like a basic state machine, which and where the idea is that you're going from reset to init state when you've had some kind of a discovery mechanism when the two sides can reach each other. Once you do that, you kind of transition into a ready to test state. And once you do that, you sequence through a whole sequence of tests. And the test that you sequence through is is something where you essentially we think we're going to identify tests with some kind of a unique ID and sort of say send test X, and the TX starts sending test X. There's a whole bunch of states which I won't go into in terms of the state machine, but the most important thing is I think we're settling in on a fairly simple register-based interface. The exact list of registers is to be settled. I think we can probably get away with 3 registers, which is sort of a command register, a status register, and a test ID. And for the most part, we're reasonably certain that both sides won't write to the same register in either of the spaces, so there should be no race conditions. Here's where we're going to borrow from D matrix in terms of the message structure. It's simply going to be like a read and write, read to a register and write from a register. So keep the interface fairly simple. We should be able to pull this off. And on the sideband interface, there is a framing bit, so we can frame these commands fairly easily. So if you go back to let me go back here, the sideband interface itself is a serial interface. So once the framing is asserted, you have a packet transmitted serially on the data interface. So it should be easy to pull off. And in a 1.1, we'll map these register commands to an I2C or an I3C.
Bappy.
Yeah.
5-minute warning.
Yep. Thank you. But so roughly this is what's going to happen. We're going to define a fairly simple register-based interface. We think we have a fairly reasonable handle on the states for bring up, and it's going to be a fairly simple narrow focus on bringing up a unidirectional link and leave bringing up both sides of a link, the management of both sides of a link to the individual controller. And we're going to borrow heavily from D matrix because this is in some sense close to being in silicon on their side. So going back to the magic picture, I think with recognizing Kash's comments about being able to map other buses for a reasonable range of use cases, I think we've got for a reasonable range of use cases around AXI, I think we've got a fairly good complete specification for an ODSA link. Any questions, thoughts? Any questions for anyone, or so all the specs, and hopefully be able to implement a complete link between chiplets.
Can you send out the slides?
Yes.
Awesome.
Okay. In that case, I think we are there any questions? Let me just go. Anybody have any questions on bus mapping or the 4 specs, or in my mind, this is a fairly big accomplishment by the group in terms of, especially if we can get this last spec written and delivered. Well, in that case, everyone, thank you. And have a good weekend and everything.
Thanks. Bye.
Thank you.